Okay everyone, we're going to do a weak acid strong base titration problem. Similar to ones we've done in class, we're going to use hydrogen fluoride or hydrofluoric acid, and we're going to titrate it with sodium hydroxide. And we have the Ka for hydrofluoric acid 6.6 times 10 to the minus 4. We're going to calculate the pH at 5 different points. At the beginning, before we've added any base, a couple of places in between the beginning and the equivalence point, at the equivalence point, and then after the equivalence point. And so each time I'm going to explain to you what process we want to use and what we want to think about. The important things to remember here are that we always take care of strong acids and bases first before we take care of any weak acid or base equilibria. And to make sure that we're keeping track of moles versus concentration, because the volume is going to change in a titration because we're adding the base from the burette, which changes the volume of our solution. Okay, so before we begin, they've told us that we have 25 milliliters of 0.3 molar HF, and they tell us we're titrating it with 0.3 molar NaOH. This is a 1-to-1 ratio, 1 proton, 1 hydroxide ion, and they're both the same concentration, 0.3 molar. So we also know we're going to get to the equivalence point at 25 milliliters of base added. So we'll just keep that in mind as we're going through this. If we have less than 25 milliliters, we're before the equivalence point. If we have more than 25 milliliters, we're after the equivalence point, and we'll treat things slightly differently. Okay, so at the beginning, the first thing we're going to do is calculate the pH of the initial acid solution before any base is added. When we're dealing with the initial solution and we haven't added any base, there's no strong acids or bases to take care of because hydrofluoric acid is a weak acid. So the only thing that we have to do is an equilibrium of that acid reacting with water, which is our Ka equilibrium. So we've got hydrofluoric acid reacting with water to form H3O plus and F minus its conjugate base. And this is a Rice table that we're going to do because this is equilibrium. And we use Rice tables for equilibrium when we don't know how much something is going to change and when we're using concentrations as opposed to moles. So we'll just put in the concentration here, which is 0.3 molar of hydrofluoric acid. Sorry. Okay. We'll subtract a little bit here, add a little bit here. That's our change. At equilibrium, we'll get 0.3 minus X. We'll have X and X in both fluoride ions and hydronium ions. And now we just have to plug these things into our Ka expression. Ka, of course, is the concentration of H3O plus times the concentration of fluoride divided by the concentration of hydrofluoric acid. And so that will be our value they've told us, 6.6 times 10 to the minus 4, and it's going to equal x squared over 0.3 minus x. It's a little bit questionable whether we can neglect x here because the Ka is about 3 orders of magnitude different from the initial concentration. So we're sort of right on the border of where we can do that. So what I'm going to do is neglect x and then iterate again to check to make sure that my assumption to neglect x was okay. So here we are. I've got this Ka and I've got 0.3 minus x. I'm going to neglect that x. So I'll take 6.6 times 10 to the minus 4 times 0.3, and then I'm going to take the square root of that so that my x will be 0.0141. Now, I want to check to make sure that my assumption was good, so I'm going to plug this x back in where I took it out. So I'll do 0.3 minus the answer times 6.6 times 10 to the minus 4, and I'll take the square root again. And my second x that I've gotten was 0.0137. This is a little bit different than the first one I got, so I'm going to try it one more time, plugging this in where I've taken it out. So 0.3 minus that answer times 6.6 times 10 to the minus 4, and the square root of that gives me 0.0137. So I'm going to call that good. 0.0137 is the answer that we need for our x. Now, what does this represent? It's actually our concentration of hydronium ions. And so to take the pH, it's just the negative log of that concentration. So I'll do the negative log of the answer, and that's 1.86. So I finished the first calculation, which is the initial pH before any base is added. So we'll move on to the second calculation. In the second calculation, we will add 10 milliliters of base. So we're going to now have to take into account this strong base reaction with the weak acid. And like I said at the beginning, whenever we have something strong, we have to take care of that first. The strong thing is going to react completely. It drives the reaction forward. So now, instead of having an equilibrium, the first thing I have to consider is actually the reaction between the acid and the base. So we have HF, and it's reacting with NaOH. And notice I'm not using an equilibrium arrow here. I'm just using the forward arrow because this reaction is going to go to completion because I have that strong base. This is going to make water and NaF, which is our salt that we get from this reaction. It turns out here sodium is actually a spectator ion, so I'm just going to write F minus over here and OH minus over here, and that should take care of us. Now, because we're doing a strong base, and we know how much the reaction is going to go forward because we know it's going to react completely because it's strong, we're actually going to use a BCA table here, which is like before, change, and after. When we use the BCA table is in a situation where we know how much the reaction is going to happen, and also in a situation where the volume is changing. And indeed here I'm adding base, which is a solution, so I'm actually going to change the volume. And when I use a BCA table, I have to use moles, not molarity, moles. So in order to begin, I need to figure out how many moles do I have of my HF. And they told me at the beginning I had 25 milliliters and that it was 0.3 molar. And so I get 0.0075 moles of HF. That's how much I have at the beginning. And now I've added 10 milliliters of base. It's also 0.3 molar. So I get 0.003 moles of OH minus that I'm adding. So that's what I'm going to start with at the beginning. 0.0075 moles here and 0.003 moles here with my hydroxide. Now, because this is a strong base, again, this reaction is going to go completely forward. It's a 1-to-1 ratio, and so I know that NaOH here is going to be the limiting reactant. I also know NaOH is going to be the limiting reactant because we haven't yet reached the equivalence point. At the equivalence point, I'll have equal numbers of moles of acid and base, but it's before the equivalence point, so the base here is our limiting reactant. So I'm going to use up all of the base that I have. And I'll end up with 0.003 moles of the conjugate base, F minus, and I'll have 0.0045 moles of my hydrofluoric acid left over. So now, what do I have? A mixture of a weak acid and its conjugate base. In other words, this is a buffer. And if I have a buffer, then I can use the Henderson-Hasselbalch equation, which is that the pH equals the pKa plus the log of the ratio of the concentrations of the conjugate base over the acid, or the log of AHA. So you can remember the conjugate base goes on the top. What do we have here? pH. We know the Ka because they told us, so this will be the negative log of 6.6 times 10 to the minus 4. That's our Ka, plus the log of the ratio of concentrations of the conjugate base over the conjugate acid, or sorry, over, the acid in this case. It's a conjugate pair. Notice, normally you have to put in the concentrations in this equation because it calls for concentrations. But because the volume is the same in both cases, I'm putting in the numbers of moles here, and it's going to work out the same because it's a ratio. In general, you want to always be careful that you're using concentrations where you're supposed to be using concentrations and moles where you're supposed to be using moles. In this case, if I divided by the total volume, which is now 35 milliliters, I would divide by 35 milliliters here and divide by 35 milliliters here. They cancel out. Okay, so I can use just moles in the Henderson-Hasselbalch equation. So now, let's calculate this out. I've got 0.003 divided by 0.0045. I'm going to take the log of that number, and then I'm going to subtract the log of our Ka, and my pH is going to be 3.00. So that's my pH after adding 10 milliliters of base. Okay, for part C, we want to know the pH after adding 12.5 milliliters of base. Now, this should sound important because we've gotten to 12.5, and we decided at the beginning that the equivalence point was at 25 milliliters, and so we're actually right now at the half equivalence point. At the half equivalence point, half of the acid has been neutralized, forming its conjugate base. So in other words, we have equal quantities of the acid and its conjugate base. Just to prove that that's true, I'll do the BCA table. Again, this is our reaction of our weak acid with the strong base. So it's going to go to completion. I'm always starting with 0.0075 moles of HF. It's the same amount that I started with before. Every time I do one of these BCA tables, I'm always starting back at the beginning because it's confusing to think, oh, now I'm adding a few extra milliliters, and it's easier to just say we start with this much. We've also now got 12.5 milliliters of base. Which is going to be 0.00375 moles. So we'll put that in here. Again, because we haven't yet reached the equivalence point, the base is a limiting reactant. It's going to react completely. And we're going to form the conjugate base over here. And now we have equal quantities of our conjugate base and our weak acid, which we can see here. And so when we look now, we've done the strong part. We have to do the equilibrium part. And this is an acid and its conjugate base, a weak acid and its conjugate base. So again, this is a buffer. And for the buffer, we're going to use the Henderson-Hasselbalch equation. And that is pH equals pKa plus the log of the ratio of the concentration of the conjugate base over its acid. And now what's going to happen to this ratio? This ratio is just 1. And the log of 1 is 0. So actually this whole term is going to be 0, and the pH will equal the pKa, which was the negative log of 6.6 times 10 to the minus 4. Which is 3.18. So now we found the pH at the half equivalence point. At the half equivalence point, the pH equals the pKa because we have equal quantities of our acid and its conjugate base. Okay, next point where we're going to calculate the pH is at the equivalence point. At the equivalence point, we will have added 25 milliliters of base. And again, it's probably unnecessary to do a BCA table here if you know that it's the equivalence point, but it never hurts to be thorough. So we'll write out that equation. Our acid plus the strong base makes water and the conjugate base. And at the equivalence point, we have equal numbers of moles of acid and base. This is just our 25 milliliters times 0.3 molar. They're going to be completely consumed, both of them, because at the equivalence point, the acid is completely neutralized. So these guys are gone, and the only thing that we're left with here is this conjugate base. Turns out the conjugate base is actually a weak base all by itself because it came from the weak acid. And so now we have to consider, since we've taken care of the strong base, what do we do with our aqueous equilibrium? If we have fluoride ions, those are going to interact with water. Making HF and OH minus. This is actually an equilibrium reaction. So we're going to need to do a Rice table. The volume won't be changing during this transformation. Now I have here the number of moles, 0.0075, and at this point I have 50 milliliters because I started with 25 and I've added 25. And so that's 0.15 molar fluoride ions. So we'll start with 0.15 molar. Some of this is going to react with the water, making the conjugate acid and hydroxide. This reaction is actually the Kb reaction for this conjugate base. So to get the Kb, we do Kw over Ka, 1 times 10 to the minus 14th over 6.6 times 10 to the minus 4. Our Kb is 1.52 times 10 to the minus 11th. Now we've done our Rice table, we're going to substitute into our Kb expression. And comparing our initial concentration to the value of Kb, they're orders of magnitude different. We can neglect our x. So we'll take our 0.15 times 1.52 times 10 to the minus 11th. And then we'll take the square root of that answer to solve for x, which is 1.51 times 10 to the minus 6. And this is equal to our concentration of OH minus. So to get the pH, first we'll get the POH, and we'll take the negative log of our answer, which is 5.82. 14 minus that gives us our pH, 8.18. And we stop and think to ourselves, does this make sense? Indeed, it does make sense because we had a weak acid, its conjugate base is a weak base. So at the equivalence point, the equilibrium reaction of this conjugate base is going to make the pH slightly more basic than neutral. Okay, the last step that we're going to do in this titration problem is to calculate the pH after we've passed the equivalence point and we've added 26 milliliters of base. So again, at this point, because we have a strong base that we're adding, we're going to do the BCA table to show the complete reaction of that strong base. And since we've passed the equivalence point, we know that we actually have more base than acid. And they told us it was 26 milliliters, and it's 0.3 molar. So that gives us 0.0078 moles of base. The acid, because it's the limiting reactant now, will be used up completely. Oops. And we'll be forming the conjugate base. Okay, so now we have a situation where we've got both hydroxide and a conjugate base. Theoretically, both of these guys are going to contribute to the equilibrium. But we just saw at the equivalence point that our weak base by itself is pretty weak. It only contributed something like 10 to the minus 6 molar concentration of hydroxide ions. So let's calculate what we get just from the hydroxide and then see whether we need to add on the contribution from that conjugate base. Okay, so now remember, this is a BCA table, so these are moles. And at this point, we've added 51 milliliters of total volume. We started with 25, we've added 26, so we have 51 milliliters total volume. So we'll take 0.0003 moles, divide by 0.051 liters, and we'll get 0.00588 molar concentration of hydroxide. And in order to find the pH, we first take the pOH. So I'll take the negative log of that answer, and that's 2.23. The pH is 14 minus that, so we get 11.77 for our pH. Now, if you remember, we said our fluoride ions before when we did the weak base equilibrium contributed something round about this 10 to the minus 6, which is out here beyond what we've taken into account with our OH minus. So it's not going to affect the pH very much. So we're going to ignore the contribution from the weak base equilibrium and just use the contribution from the strong base. So our final pH here at 26 milliliters will be 11.77.